That's sort of the end game, to be able to write code like that and more. But let's really start back at the beginning and see how we can't get from zeros and ones that computers speak all the way back to artificial intelligence. So computer science is in the name of the course, Computer Science 50. But what is that? Well, it's really just the study of information. How do you represent it? How do you process it? And very much germane to computer science is what the world calls computational thinking, which is just the application of ideas from computer science, or CS, to problems, generally in the real world. And in fact, that's ultimately, I dare say, what computer science really is. It's about problem solving. And even though we use computers, you learn how to program along the way, these are really just tools and methodologies that you can leverage to solve problems. Now, what does that mean? Well, a problem is perhaps most easily distilled into a simple picture like this. We've got some input, which is like the problem we want to solve, and the output, which is the goal we want, the solution there too. And then somewhere in the middle here is the proverbial black box, the sort of secret sauce that gets that input from output. So this then, I would say, is, in essence, is problem solving, and thus computer science. But we have to agree, especially if we're going to use devices, Macs, PCs, phones, whatever, how do we all represent information, the inputs and the outputs, in some standardized way? Is it with English? Is it with something else? Well, you all probably know, even if you're not computer people, that at the end of the day, computers somehow use zeros and ones entirely. That is their entire alphabet. And in fact, you might be familiar already with certain such systems. So the unary notation, which means you essentially use single digits, like fingers on your hand. For instance, unary, aka base 1, is something you can do on your own human hand. So for instance, with one human hand, how high can I count? All right, so hopefully 1, 2, 3, 4, 5. And if you want to count to 6 and to 11 and 10 and so forth, you need to, take out another hand or your toes or the like, because it's fairly limiting. But if I think a little harder, instead of just using unary, what if I use a different system instead? What about something like binary? Well, how high, if you think a little harder, can you count on one human hand? So 31, says someone who studied computer science before. But why is that? It's kind of hard to imagine, right? Because 1, 2, 3, 4, 5 seems to be the 5 possible patterns. But that's only when you're looking at the totality of fingers that are actually up, 5 in total, or 4 in total, or 1, or the like. But what if we take into account the pattern of fingers that are up, and we just standardize what each of those fingers represent? So maybe we all agree, like a good computer would too, that maybe no fingers up means the number 0. And if we want to count to 1, let's go with the obvious. This is now 1. But instead of 2 being this, which was my first instinct, maybe 2 can just be this, a single second finger up like this. And that means we could now use 2 fingers up to represent 3, I'll propose. We can use just 1 middle finger up to offend everyone, but represent 4. I could maybe use these 2 fingers with some difficulty to represent 5, 6, 7. I'm already up to 7, having used only 3 fingers. And in fact, if we keep going higher and higher, I bet I can get as high as 31 for 32 possible combinations. But the first one was 0, so that's as high as we can count. So we'll make this connection in just a moment. But what I started to do there is something called base 2. Instead of just having fingers up or fingers down, I'm taking into account the positions of those fingers and giving meaning to, like, this finger here, this finger here, this finger here, and so forth. Different weights, if you will. So the binary system is indeed all computers understand. And you might be familiar with some terminology here. Binary digit is not really something anyone really says, but the shorthand for that is going to be bit. So if you've heard of bits, and we'll soon see bytes, and then kilobytes and megabytes and gigabytes and terabytes and more, this just refers to a bit, meaning a single binary digit, either a 0 or a 1. A 0 is perhaps most simply represented by just like turning, maybe keeping a finger down, or in the world of computers, which have access to electricity, be it from the wall or maybe a battery, you know what we could do? We could just decide sort of universally that when a light bulb is off, that thing represents a 0. And when the light bulb is on, that thing's going to represent a 1 instead. Now, why is this? Well, electricity is such a simple thing, right? It's either flowing or it's not. And we don't even have to therefore worry about how much of it is flowing. And if you vaguely remember a little bit about voltage, we can sort of be like 0 volts. Nothing's there available for us. Or maybe it's 5 volts or something else in between. But what's nice about binary, only using zeros and ones, is that it maps really nicely to the real world by like throwing a light switch on and off. You can represent information by just using a little bit of electricity or the lack thereof. So what do I mean by this? Well, suppose we want to start counting using binary. Zeros and ones only. Well, let's think of them metaphorically as like akin to these light bulbs here. And in fact, let me grab a few of these light bulbs, and let me propose that if we want to represent the number 0, well, it stands to reason that here, single light bulb that is off can be agreed upon as representing 0. Now, in practice, computers don't have little light bulbs inside, but they do have little switches inside. Millions of tiny little things called transistors that, if turned on, can allow it to capture a little bit of electricity and effectively turn on a metaphorical bulb. Or the switch can go off. The transistor can go off and therefore let the electricity dissipate, and you have just now a 0. Unfortunately, even though I can let some electricity, here's the battery I mentioned is required. Even though we might have some electricity available to us, I can therefore count to 1. But how do I go about counting? Hardware problem. How do I go about counting higher than 1 with just a light bulb? Yeah, so I need more of them. So let me grab another one here. And now I could put it next to it. And this 2, I'll claim, is just still the number 1. But if I want to turn 2 of them on, well, that would mean I could count to 2. And if I maybe grab another one, now I can count as high as 3. But wait a minute. I'm doing something wrong. Because with 3 human fingers, how high was I able to count? So 7 in total, starting at 0. So I've done something wrong here, but let me be a little more clever then about the pattern that I'm actually using. Perhaps this can still be 1, but just like my finger went up and only one finger in the second version of this, this can be what we represent as 2. Which one do I want to turn on as 3? Your left or your right? So you're right, because now this matches what I was doing with my fingers a moment ago, and I claimed we could represent 3 like this. If we want to represent 4, that's fine. We have to turn that off, and this on, and that's somehow 4. And let's go all the way up to 7. Which ones need to be on to represent the number 7? All right, so all of them here. Now, if you're not among those who just sort of naturally said all of them, like what the heck is going on? How do half the people in this room know what these patterns are supposed to be? Well, maybe you're remembering what I did with my fingers, but it turns out you're already pretty familiar with systems like this, even if you might not have put a name to it. So in the human world, the real world, most of us deal every day with the so-called base 10 system, otherwise known as decimal, dec implying 10, because in the decimal system, you have 10 digits available to you, 0 through 9. In the binary system, we only had 2, bi implying 2, so 0 and 1. And unary, we had just 1, a single digit there or not. So in the decimal system, we just have more of a vocabulary to play with. And yet, you and I have been doing this since grade school. So this is obviously the number 123. But why? It's technically just 3 symbols, 1, 2, 3. But most of us, your mind immediately goes, OK, 123. Pretty obvious, pretty natural. But at some point, you, like me, were probably taught that this is the ones place, and this is the tens place, and this is the 100s place, and so forth. And the reason that this pattern of symbols 1, 2, 3 is 123 is that we're all doing some quick mental math and realizing, well, that's 100 times 1 plus 10 times 2 plus 1 times 3. Oh, OK, there's how we get 100 plus 20 plus 3 gives us the number we all know mathematically is 123. Well, it turns out whether you're using decimal or binary or other base systems that we'll talk about later in the course, the system is still fundamentally the same. Let's kind of generalize this away. Here's a 3-digit number in some base system, specifically in decimal. And I know that only because of the placeholders that I've got on top of each of these numbers. But if we do a little bit of math here, 1, 10, 100, 1,000, 10,000, and so forth, what's the pattern? Well, technically, this is 10 to the 0. 10 to the 1, 10 to the 2, and so forth. And we're using 10 because we can use as many as 10 digits under each of those columns. But if we take some of those digits away and go from decimal down to binary, the motivation being it's way easier for a computer to distinguish electricity being on or off than coming up with like 10 unique levels of electricity to distinguish among. You could do it. It would be annoying and difficult to build in hardware. You could do it. So much simpler to just say on and off. It's a nice, simple world that way. So let's change the base from 10 to 2. And what does this get us? Well, if we now undo the math, that's 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4. So the mental math is now about to be the same, but the columns represent something a little bit different. So for instance, if I turn all of these off again, such that I've got off, 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 otherwise known as 0, 0, 0. It's 0 because it's 4 times 0 plus 2 times 0 plus 1 times 0 still gives me 0. By contrast, if I turn on maybe just this one all the way over on the left, well, that's 4 times 1, because on represents 1 and off represents 0, plus 2 times 0 plus 1 times 0, that gives me 4. And if I turn both of these on such that all 3 of them are now on, aka 1, 1, 1, that's 4 times 1 plus 2 times 1 plus 1 times 1. That then gives me 7. And we can keep adding more and more bits to this. In fact, if we go all the way up numerically, here's how we would represent in binary the number you and I know as 0. Here's how we would represent 1. Here's how we would represent 2 and 3 and 4 and 5. And you can kind of see in your mind's eye now, because I only have 0s and 1s and no 2s or 3s, not to mention 9s, I'm essentially going to be carrying a 1 in a moment if we were to be doing some math. So to go from 5 to 6, that's why the 1 ends up in the middle column. To go to 7 here gives us now 1, 1, 1, or on. How do I represent 8 using 1s and 0s? Yeah. Yeah, so we're going to need to add another digit. We need to throw hardware at the problem using an additional digit so that we actually have a column representing 8. Now, as an aside, and we'll talk about this before long, if you don't have an additional digit available, if your computer doesn't have enough memory, so to speak, you might accidentally count from 0, 1, 2, 3, 4, 5, 6, 7, and then accidentally end up back at 0. Because if there's no room to store the 4th bit, well, all you have is part of the number. And this is going to create all sorts of problems then, ultimately, in the real world. So let me go ahead and put these back and propose that we have a system now, if you agree to sort of count numbers in this way, via which we can represent information in some standard way. And all the device underneath the hood needs is a bit of electricity to make this work. It's got to be able to turn things on, aka use some transistors. And it's got to be able to turn those things off so as to represent 0s instead of 1s. But the reality is, like, 2 bits, 3 bits, 4 bits aren't very useful in the real world, because even with 3 bits, you can count to 7. With 4, you can count to 15. These aren't very big numbers. So it tends to be more common to actually use units of measure of 8 bits at a time. A byte is just that. 1 byte is 8 bits. So if you've ever used the vernacular of kilobytes, megabytes, gigabytes, that's just referring to some number of bits. But 8 of them together compose 1 individual byte. So here, for instance, is a byte worth of bits, 8 of them total. I've added all the additional placeholders. And what number does this represent in decimal, even though you're looking at 8 binary digits? It's just 0, because like literally every column is a 0. Now this is a bit more of mental math, but unless you know it already, what if I change all of the 0s to 1s? I turn all 8 light bulbs on. What number is this? Yeah, so 255. Now, those of you who didn't get that instantly, that's fine. You could certainly do the math manually. I dare say some of you have some prior knowledge of how to do this sort of system. But 255 means that if you start counting at 0 and you go all the way up to 255, OK, that's 256 total possibilities once you include 0 in the total number of patterns of 0s and 1s. And this is just going to be one of these common numbers in computer science. 256, why? Because it's referring to 8 of something. 2 to the 8 gives you 256. And so you're going to commonly see certain values like that. 256, back in the day, computers could only show 256 colors on the screen. Certain graphics formats nowadays that you might download can only use as many as 256 colors because, as we'll see, they're only using, for instance, 8 bits. And therefore, they can only represent so many colors of the rainbow as a result. So this then is how we might go from just 0s and 1s, electricity inside of a computer, to storing actual numbers with which we're familiar. And honestly, we can go higher than 255. What do you need to count higher than 255? A 9th bit, a 10th bit, an 11th bit, and so forth. And it turns out common conventions nowadays, and we'll see this in code too, is to use as many as 32 bits at a time. So that's a good chunk of bits. And anyone want to ballpark how high you can count if you've got 32 bits available to you? Oh, fewer people now. Yeah, in the back. Yeah, so it's roughly 4 billion. And it's technically 2 billion if you also want to represent negative numbers, but we'll revisit that question. But 2 to the 32nd power is roughly 4 billion. However, nowadays it's even more common with the Macs and PCs you might have on your laps and even your phones nowadays to use 64 bits, which is a big enough number that I'm not even sure offhand how to pronounce it. That's a lot of permutations. That's 2 to the 64 possible permutations, but that's increasingly commonplace. And as an aside, just to dovetail things with our discussion of AI, among the reasons that we're living through over these past few years, especially this crazy, interesting time of AI, is because computers have been getting so much faster, exponentially so over time. They have so much more memory available to them. There's so much data out there on the internet in particular to train these models that it's an interesting confluence of hardware now actually meeting the mathematics and statistics that we'll talk about later in the class that ultimately make tools like the cat we just built possible. But of course, computers are not all math. And in fact, we'll use very little math per se in this class. And so let's move away.